السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Last time we started to talk about first order logic, I think even from the one before, and we covered the main concepts of first order logic, saying that we have objects, we have relations between objects, we also have functions, okay, and we can construct atomic sentences from these entities, and we can also construct complex sentences from connecting these sentences using the connectives, the regular connectives, the Boolean, the logical connectives like and or not, or also the quantifiers like the universal quantifier and the existential quantifier. And towards the end of the lecture, we talked about some properties of the quantifiers, like that we can switch two similar quantifiers together, but if the quantifiers are not the same, like for all and they exist, we cannot switch them. Okay, and we also talked about the fact that we can define one quantifier using the other. We can represent one quantifier using the other with the help of the Morgan laws. Today we'll talk briefly about another property of first order logic, but then we will focus more on how to use first order logic in representing knowledge bases. Okay, I think we will inshallah cover two different domains or two different examples. First, let's talk about equality. We kind of went through that last time when we were talking about the syntax of first order logic, and we said that equality is one way of constructing atomic sentences, like saying term 1 equals term 2. We said that this is true if term 1 and term 2 both refer to the same object. Okay, now let's see how we use this equality property or equality sentence in some definitions. So if I want to define the predicate sibling, okay, in terms of parents, and let's assume that we have the predicate parent that says that X is a parent of Y, so a parent of, let's say that we have parent of XY, and that means, the semantic of it means that X is a parent of Y. Okay, now we want to define sibling, the relationship sibling. Okay, how can we define it? One way of defining it, only using parent, is this way. Okay, so let's take this way, or this complex sentence step by step. So first, we define the predicate sibling, okay, which means X is a sibling of Y, this way. Now, first, what is the meaning of sibling? I think you know that sibling means a brother or a sister. Okay, if someone is a brother of me or sister of me, then he or she is a sibling of me. Okay, but here we don't have brothers and sister, and we have only parent. Okay, so we have the predicate parent or the relation parent, and using it, I want to define sibling. So I will define it that way. First, forget about this part. Okay, imagine that it's not there. And let's see how we define sibling. We define sibling, two persons are sibling of each other if they have the same parents. Right, that's logical. So how can we say it that way in first order logic? We say that there is two persons, M and F. Okay, again, forget about this part. Okay, imagine that they are not there now. Okay, so there is two persons, M and F, such that M is the parent of X and F is a parent of X. So that means that M and F are parents of X, sorry, and also M and F are parents of Y. So if I have the same parents, so that's what this definition is saying. If I have the same parents, like someone else, then we are siblings. Okay, I think this is clear. Now, what is the problem with this definition? The problem is that we didn't say that M and F are two different persons. We have to have the same two parents so that we can be siblings. Okay? If I didn't say that M and F are two different persons, which this sentence currently doesn't say, it says M and F. M can be F, can refer to the same person like F, okay, generally. If that's the case, then we are talking about one parent. We are not talking about two parents. So to make sure, to enforce the fact that they have to be two different parents, which means mother and father, then we have to say that M is not equal to F. In first order logic, we cannot just say M is not equal to F. We don't say it that way. Okay, so we don't use this. We say not M equal F. Okay, not M equal F. So M equal F here is a sentence that is true if M and F are the same, are referring to the same object. So here with the not, we say that M is not referring to the same object like F. So that means M is not equal to F. Okay. Similarly, we have to say that with the current definition, X and Y can also be the same person. Okay, so we have to say that they are two different persons. So we have to say that X and Y are not the same person. So we have to say not X equals Y. Okay, so that's now the definition of siblings. They are, for all X and Y, for any two persons in the world, these two persons are siblings if and only if they are different. Remember that X and Y here are variables. Okay, so we have to explicitly say that they are different if we want to enforce, if we really mean that. Okay, so these two persons are different, and this whole thing. So there are two conditions here. This is the first one, and that's the second one. Okay, so the second one is that X and Y now have the same two parents, and they are different also. And the parents are different. Okay, so M and F are different. So there exist M and F such that M and F are the parents of X, and M and F are parents of Y, and also M is not equal to F. Any questions about this? Yes, Faisal. Yes. Okay, we cannot do that here because parent is not a function. Parent doesn't refer to an object. Parent is a relation. If you define parent as a function, yes, you can do that. But in that case, you don't say X value. You say just parent M, parent of M. Okay, and that will refer to one parent of M. Sorry, parents of X in this way. That will refer to one of the parents of X. But in this example, parent is a relation, not a function. Okay, is that clear, Faisal? Exactly, yes. Okay, so this is exactly. Yes. Okay, good question. Any other questions? So notice the difference between a function and a relation. The relation is true or false. Okay, the relation is true or false. So you can use the relations. You can connect the relations with logical operations like AND here. But functions are not true or false. Functions are pointers to objects or references to objects. Okay. Later in this lecture, we will use functions. We'll see how they are used also. Any other questions? No questions means everything is good, hopefully. Okay, then we'll switch to the next set of slides, mainly about using first order logic. Let me share that. Okay, I think you see it now. Yes? Okay. Okay, so as I told you earlier, we will focus on in this session on how to use first order logic. We already saw an example in the previous slide when we defined siblings, but we'll see more examples in this set. So the first example is extension of what we just mentioned about kinship, or about the relations in a family. Okay, so now we'll focus more on the domain of a family. How can we define relations in a family? So first we define some quick definitions, or easy definitions, something like brothers are siblings. Since we defined what siblings are, okay, then X and Y are brothers. If X and Y are brothers, then they are also siblings. Okay, so that's kind of a rule. If X, Y are brothers, then they are siblings. We can also say that siblings, things like the symmetric relations. So sibling is symmetric, right? So if X and Y, if X is a sibling of Y, then Y is a sibling of X. That might look really trivial, or you might think why we are doing that. But remember that predicates that refer to relations, of course, takes the variables in order. Takes the arguments in order. So sibling of X, Y here means that X is sibling of Y. Okay? The system by default doesn't know that it is the same thing like saying that Y is sibling of X. We know that, but we have to tell the knowledge base this fact. Okay? So we have to define it that way so that it knows that it is symmetric. It doesn't matter, the order doesn't matter. Okay? But it's not by default. We have to tell it. We have to explicitly mention it. Okay? So this is a way of doing that, to say that for any two persons, if these two persons are siblings, actually this is not the meaning of the predicate. If the first is a sibling of the second, then the second is a sibling of the first. Okay, that's what this sentence means. Now let's get a bit more complicated, and let's represent this rule. One's mother is one's female parent. Okay, so here we have we assume that we have two things defined. A female, the concept of being a female, and parent relation. Okay, and I want to use these two to define what one's mother is. Okay, so here is how. Look at this. What does this mean? For all M and C, that means that for any two persons in the world called M and C, if the mother of C equals to M, if and only if M is female and M is the parent of C. Okay, so M is the mother of C if and only if M is a female and M is the parent of C. Okay, now look at this sentence and tell me what is mother and what is female, and what is parent. We said that parent is a relation before, right? So this is binary relation. We said that already. How about mother here, and how about female here? Faisal? So let's start with female. Female is unary relation. It is an attribute. It's like a property, right? So that's a unary relation. So that's like whether M is a female or not, right? So that's unary relation. That's correct. Now, how about mother here? It is a function. Why is that? Yes, because it's not because it's giving us an object M, because it refers to an object that is equal to the object, that is the same object that M refers to. Okay, so mother here is a function. Mother of C is a function that refers to an object that represents the mother of C. Now we say that mother of C is M, and we give it another name. Yani, remember from last time we said that a sentence can be term equal term. Okay, term equals term means that both are referring to the same object. You can look at it in a different way. You can say that both are two names of the same object, because they are actually names that refer to the same object. Okay, so what this sentence is telling us is that the mother of C is M, or is called M here, is M, if and only if this condition is satisfied. What is that condition? M is female and M is the parent of C. Okay? So this rule applies to any two persons in the world. So for any two persons, one is the mother, the second is the mother of the first, the first is the mother of the second, because the order here M and C. The first is the mother of the second, if and only if the first is a female and the first is the parent of the second. That's the definition. Okay, so you need first to understand the relationship or the rule that you want to express, then see how to express it using what you know already, what you defined already as predicates and as functions. Okay, and here, by the way, M is a term, of course, or a variable. Okay, it's a term, and mother of C as a whole is another term. So mother is a function, mother of C is a term. Term means something that refers to an object. Okay, so this sentence has all the elements, the main elements in first order logic. Any questions about this? Okay. Now let's move on to another one that might look a bit more complex. Now let's define cousins. Let's define cousins. We know that a cousin is a child of a parent's sibling. Okay, what does that mean? If I have two persons like that, let's say here X and Y, one of the parents of X, let's say that this is the parent of X, and that's the parent of Y. If these two parents are siblings, okay, so that's sibling, then X and Y are cousins, right? That's the relationship that's called cousins. Okay, in Arabic, ابن الخال أو ابنة الخال أو ابن العم أو ابنة العم. Okay, that's cousin. So cousins have parents who are siblings, right? Now, how can we write that using first order logic? Okay, someone other than Faisal. It seems like there are more students, right? Anyone other than Faisal? Just try. We are trying together. Anyone? How can we write something like this? We should write it in steps, of course. We can write it in steps. Okay, so we have two steps here. We have two levels here, right? We have parents who are siblings. Okay, and then we have the two persons. Okay, and that's the definition of cousins. So we have to first say that these two persons have parents and these parents and siblings, and then that defines the relation cousins. How can we do that? Anyone? Let me call names then. Said? Said? Are you with us? Hello? Said? I saw your mic and then it disappeared. No, I didn't hear you. Said? طيب, how about Hamza? Hamza Salah? Hamza Salah? Hamza? Hamza, can you pick up the mic, please, and tell me how we can express this in first order logic? We can do it together. Yeah. We are towards the end of the semester, Hamza. Okay. Anyone else? Mustafa? Any of the Mustafas? Okay, Mustafa Gindi. Wa alaikum assalam wa rahmatullahi wa barakatuh. Thanks for saving me. Okay, we'll see. Yes, so let's say that we have two parents. We call them okay, P1 and P2. Okay, so we have to say that what are the relations here that we can say, that we can use? So P1 is the parent of X, right? No, let's define the parent relationships first. Okay, so parents, we can say P1X. Okay, and we also have parent P2X. Very good. So we have now these two parents, and we want to say that these are siblings. So we can say sibling of what? P1 and P2. Okay, so these are the predicates that we will use. Okay, and of course we have to use eventually cousin. That's what we want to define. So cousin X and Y, right? Okay, so this is the first step in writing any of these expressions or sentences, to define what are the predicates and functions that we want to use. Now, let's compose together the parts of the sentence. So we want to define cousins, right? So we have to say cousin XY, if and only if, right? and then we will put the definition here. And to do that, we have to say for all x and y. So any two persons, x and y, these two persons will be cousins if and only if something will happen. What is that? So we should put the conditions here. What are the conditions, Mustafa? Okay, so what is P1 and P2? We have to define them, right? So we have to say they exist, right? P1 and P2. So because these are two different persons, right? I mean, two persons other than x and y. So there exist P1 and P2 such that what? What should we write here? They are siblings first. Okay, so we can say sibling P1, P2. Okay. That's it? Yes, what is missing? So we use this, we use this. How about these two? We did that already يا مصطفى. We did the instantiation here. Okay, kind of we used the existential quantifier here because for these two cousins there is two parents, right? So that's why we said that they exist here, P1 and P2, and you said that P1 and P2 are siblings. But that's not enough for x and y to be cousins. What is missing now? Yeah, these two are missing, right? Are missing. So how can we add them here? And very good. Parent of P1 comma, okay, sorry, x, okay. So now P1 is a parent, yes, and parent P2, comma, okay, so this should be y, yes, so, comma y. So that's now the condition as a whole. Okay, put this here. Is there anything missing? Yes, so that's now the condition. So x and y will be cousins if and only if there exist two persons, P1 and P2, such that P1 and P2 are siblings, and P1 is the parent of x and P2 is the parent of x. Okay, thanks, Mustafa. Did you see it hard, Mustafa? Yes, you have. Yes, exactly. So you have to, don't think about it as at once. You have to decompose it into small parts with the predicates and the functions, and then you compose them together to show the whatever you want to show, the definition or whatever. Okay, thanks, Mustafa. Thanks. So you saved me, you didn't sink me. Okay, any questions about this? So now let me show it the way that I wrote it in the slide. Which is this. Okay. So cousins xy, if and only if there exist P and PS. So here we use P1 and P2. Parent P is parent of x, PS is parent of y, and both are siblings. Okay, now let's switch to the second example. We said that we have two examples, or two domains. So the first one was the kinship. Of course, kinship has much more than that, right? So you will see that in the textbook. You will see that also in the homework, inshallah. And you can play with that. The second example, or the second domain, is the Wumpus wallet. Okay, remember the Wumpus wallet that we started earlier? Now, we want to see how we can use first order logic to represent sentences in the Wumpus wallet. And before I want to do that, I want you to understand or to remember always the context of what we are doing. Why are we doing that? Why are we trying to use first order logic to represent something in these examples? Remember, the context was that we want to build an agent that can make decisions. And one way of building an agent that can make rational decisions is to use knowledge base. To use the knowledge base, we have to represent the sentences in the knowledge base in a way that from which we can infer the best actions or the decisions that we will make and the knowledge that we know. Okay? In session 5, we proposed, or we studied how we can use propositional logic to represent sentences in the knowledge base. And we also saw a couple of examples of how we can infer or we can entail new sentences from the knowledge base. We saw model checking, and we saw also the resolution algorithm. Okay? And both infer sentences from existing ones. And then we said that propositional logic is restrictive. It's not very powerful in terms of expressing the sentences. So we switched to another example of languages in which we can write or we can represent sentences in the knowledge base with, which is first order logic. So in first order logic, we use entity, we use objects, we use relations, we use functions to represent the sentences in the knowledge base. Okay, we went through the first example, which is kinship. Now we want to see how we can use first order logic to represent what we know about the Wumpus wallet. Next lecture, inshallah, we will see how we can infer. Inshallah, we'll go through at least one example of inference algorithm by which we can do inference over the knowledge bases that are written in first order logic. So that's again quickly the context of what we are studying here. Now, the Wumpus wallet, we want to represent the sentences or what we know about the Wumpus wallet. First thing to do is to represent the perceived signals. Okay, every time step, the agent perceives some signals from the environment, from the Wumpus wallet. Okay, so we define a predicate, percept, and this predicate takes the perceived signals and the time, and it indicates that these signals are perceived at that time. And now we want to say that whatever we perceived in terms of stench or breach, if we perceived glitter, okay, then we want to explicitly identify by itself that we perceived glitter at time t, because that will be much more important now than any of stench or breach signals. Okay, so if we perceived anything in terms of stench or breach besides glitter, so notice that glitter here is constant, but stench and breach are here variables. Okay, and we quantify these variables here. So that means that for any value of S and B, whether we have stench or not, whether we sensed stench or not, whether we sensed a breach or not, once we sense glitter, then I will activate the predicate glitter by itself. So here we have another predicate called glitter. Right. Why I want to do that? Because of the second sentence here. I want to say that once I sense glitter, then the best action to do at that time is to grab the gold, because as you know, glitter at any time means that the gold is at that room, which means that I should grab it now. Okay, so best action here is a predicate, okay, that takes an action and time. Okay, so this sentence means that if I sensed glitter at time t, so if glitter t is true, if glitter t is true, which means if I sensed glitter at time t, remember these meanings or these interpretations or these semantics, you as a designer has to define. Okay, remember, whatever language that we are using, whether it's proposition logic or first order logic or whatever, we have to define the semantics. It's not just syntax. Syntax by itself has no meaning, is meaningless. Okay, you have to define the semantics behind every predicate, every function, every constant that you use in the knowledge base. So glitter of t means that you sense it, or the agent sensed glitter at time t. So if the agent, so this rule means at any time, if the agent sensed glitter at that time, then the best action to do is to grab, which means grab the gold at the location where you are in now. Okay, so this is another example of rules, of expressing rules in the Wumpus world. Now let's move on to other types of rules and talk about the properties of squares or rooms. Okay, remember in the Wumpus world, we call the squares also rooms. So here I want to define how or what room is adjacent to another room. What do you mean by adjacent rooms? You might think, this is really silly, right? This is very trivial. We know that this room is adjacent to that room. We as humans know that, but we have to define it to the system that we are building. We have to define it explicitly. Okay, so which room is adjacent to the other? Because we will use that. If you remember the rules of the Wumpus world, whenever there is a pit, then we sense a breach in one of the adjacent rooms. Whenever there is a Wumpus, we sense a stench in one of the adjacent rooms. So we have to define what adjacent means. So we don't just come up with some random predicates. We define predicates based on our needs, based on our knowledge, our now humans' knowledge about the world. We model it that way. Okay, so I hope one of the concepts that you come up with out of this course is that we have two things here. We have a world, we have the real world, of course assuming that the Wumpus is a real world, and we have a model. And big part of what we are doing in AI is to have a good model of the world. If we have a good model of the world, then we can make good decisions in the real world. Okay? But if that model is not a good representation of the world, then we are wasting our time. Okay? Because we are imagining that something that's much simpler than or much useless, or it will be useless in terms of the real world, or in terms of the real scenarios that we see in the world. So now there is a need to define adjacent rooms. So how can we define adjacent rooms? We have the predicate adjacent that takes two rooms with their coordinates, and two rooms will be adjacent to each other if and only if they are there is one difference in one of the two dimensions. Okay, so AB will be adjacent to XY if AB belongs to one of these four elements in that set. It's either x plus 1 y or x minus 1y, or x y plus 1, or x y minus 1. So it's simply this way. If this is x and y, then it is one step in one of these 4 dimensions. And that's for any 4 coordinates x, y, a, b. So for any of these 4 coordinates, x, y will be adjacent to a, b, if and only if a, b is one of these 4 things. Okay? By the way, you can say also a equal to x plus 1, or a equals, you can name it. So there are multiple ways, of course, to express the same thing in first order logic. Okay, you can do it that way also. Now, if another property of squares is that if the agent is at room Q at time t, so that's what at means. So the agent is at room Q at time t, and the agent sensed breeze at that time, then we can call the room to be breezy. So now breeze is a predicate, okay, that takes time t and indicates whether we sensed breeze or not. But it has nothing to do with a location, with a room. So this rule tries to connect what we sense with where we are now. Okay? Again, it might be trivial to us, but we have to explicitly mention that in the knowledge base so that we can use that rule in inference. So if the agent is at room Q at time t and the agent sensed breeze, then this room is considered breezy, and that's the definition, that's the meaning of breezy of Q. Now, based on that, we can define what we call a diagnostic rule. We can infer cause from effect. So what is the cause here and what's the effect? The cause here is that we have a pit, okay? And the effect is that we sensed breeze. So given the effect, we can infer the cause. If we sensed, if one of the rooms is breezy, which means that we sensed breeze when we are at that room, at that time, then now this is the cause. Then there is a pit somewhere in the adjacent rooms. So the first step actually, when you design these rules, you have to write the rules in natural language first and think about them, and then you interpret them using first order logic. So the idea here is that if one of the rooms is breezy, then that means that the pit is somewhere around. How can we say that the room is breezy? Using breezy of Q. That's what we defined here. Okay, so that's what we defined here. That's breezy of Q. How can we say that there is a pit somewhere around? We can use two predicates here. First one, that there is a room that is adjacent to Q, and the pit is in that room. Okay? So this is the effect. Observing the effect. So that's a very common example of inference and a need for inference. Okay? The relation between cause and effect. Of course, cause is leading to the effect, right? Right? So sometimes we see the cause, then we infer that there will be an effect. And other times we see the effect and we want to infer the cause of that effect. In this case, we see the effect, we sense the breeze, then we infer that infer the cause. And the cause here is that there is a pit in one of the adjacent rooms. The other way, so we call this diagnostic rule. Why is it diagnostic? Okay. By definition, diagnostic means that I see something, I try to think what is the thing that caused this. Okay, so we infer cause from the effect. We see the effect, we infer cause. The other way around is called causal rule. Causal rule. Okay. Oh, sorry. Okay, so in the causal rule, we infer the effect from the cause. That's easier, right? So this rule means if we have a pit at room R, then we will smell, or there is a smell of breeze in one of the adjacent rooms. So there is a room that is adjacent. There is a room that is adjacent. Okay, and if that room is adjacent, then we will smell breeze at that room. Okay, so the meaning of this rule is that if there is a pit at room R, then if a room is adjacent to Q, then we will smell breeze at that room. Okay, so that means that there is at least one room, in every adjacent room, that's why we have for all here. Okay, so in every adjacent room, we will smell breeze at this room. Okay, any questions about this? Any question about anything in the lecture today? Do you hear me? Okay, no questions? So you understand everything? If I make a surprising quiz now, everything will be okay? Should we make a quiz now? Because I see the attendance, yani mashallah, it's great attendance. Okay, Yusuf, I didn't hear you for a while. Any questions, Yusuf? Yusuf, are you with us? Yusuf, pick up the mic, please. Wa alaikum salam wa barakatuh. Where are you, Yusuf? Okay, I used yani, to hear your voice a lot. Okay, just wanted to check yani, that you are okay, inshallah. Okay, and where is Mahmoud also? Mahmoud is not, I don't see him recently much in class. Is he okay? Anyone knows Mahmoud? No, there is another Mahmoud, if I remember correctly. Anyway, if also Abdurrahman, I don't see him much, and Hamza, I don't see him much. Okay, I hope that you will hear me in the recording and will show up inshallah next class. Any questions before we stop? So we still have, I think, one more slide in this set of slides, and then inshallah next time we will talk more about how we can do inference using first order logic. Hopefully inshallah we will be done with first order logic in the next lecture, and then we will switch to probabilistic inference inshallah from Tuesday. Okay, if there are no questions, then we will stop here, and inshallah wish you a great weekend inshallah. So talk to you on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.